All right, so this is kind of where I left off on Friday. Just thinking about two different kinds of water management. Supply side water management, which involves things like increasing the efficiency of your piping system, minimizing leaks, also making sure that contamination doesn't get into your water supply, expanding your water system, building more dams, building more wells, building more pipes and aqueducts to transport water where it needs to go, recycling wastewater, treating wastewater, but also designing systems so that you can maybe reuse certain kinds of water for lower value uses. We saw that was the case in Israel. Building new kinds of water supplies like desalination plants. On the demand side, there's information campaigns, which are just kind of pleas from the authorities to use less water. There's an example of this in South Africa when they were forecasting that they might run out of water. They never actually did, but it was a concern, and they were kind of like gauging their water supplies very closely, and in some cases urging, like this article says here, urging their citizens to consume less. And that works to some extent, maybe for some people who have strong consciences, but like this says here, more than half the residents ignored those voluntary restrictions just because there's nothing at stake. You don't get any sort of punishment or reward for complying with what those requests are. We talked about behavioral nudges being one where maybe if you put people's water consumption relative to their neighbors on their water bill, they might decide, oh look, I'm using much more water than people around me are. I should maybe consider what I'm doing a little bit better. You might hire water cops to go around and make sure people don't have sprinklers on their lawn. Banning certain kinds of outdoor uses of water, for example, are commonly used to manage demand. But there's also this price mechanism, which is a pretty wonderful thing in the way that it gives direct incentives to people. It rewards people for using less, and it penalizes people for using more. And it also gives people options. It gives people choices to decide what's the portfolio of their income that they want to spend on water versus other things. How valuable is water to them versus other things, and they can sort of decide that for themselves. And I just wrote this note here at the bottom. This is figure 20.9 in the textbook, which has a graph of, I believe it's water bill, sort of the average water bill of a household on the y-axis, and then precipitation on the x-axis. And it kind of just shows that there's not very much of a relationship at all between what the water scarce environment is of a United States city and how much they charge for water. It's mostly a political decision. It's sort of been funneled through the political process, and people decide on those water rates based on what they can negotiate in the political sphere. And it doesn't really have that much to do with the true water scarcity. So one thing that we might do, just a simple measure to reform water policy, would just be to price water according to how scarce it actually is. Definitely in the West, in places where they're draining aquifers and lakes at a pretty rapid rate. In those cases, yeah, it would make a lot of sense to increase the price and cause people to actually kind of bear some of the costs of the scarce water that they're using up. And then in the East, in the Eastern United States, and particularly in places that get a lot of rain and have vast water supplies, prices wouldn't need to be as high because water, isn't as scarce of a resource in the Eastern United States as it is in the West. But I would encourage you to look at this figure 20.9 in the book and read kind of the discussion around it, as it kind of just talks about how there's not that much actual relationship between the price of water and the water quantity that's available in the environment nearby the cities, either in the lakes and the streams or in the groundwater aquifers. So the first principle I just mentioned was that water pricing is a nice tool. It's at least a good idea, to consider. It's not maybe the absolute final word, but it's I think a leading candidate for how to manage demand and how to make sure water gets allocated to where it's most highly valued. The other way is allowing water to be transferred between different sectors of the economy. So water marketing is something that could go a long way towards ensuring that water is being put to use in the most beneficial ways. This is a figure from the book, from chapter 20, again from the textbook, that shows some of the gaps between the values of water in particular uses. So values, I have these highlighted here, these domestic and industrial uses. There's average values per acre foot. AF is acre foot, the amount of water that it would take to cover an acre of land with a foot of water. So these are average values per acre foot and also median values per acre foot, just different summary measures. But the main point is that, you know, the water in industrial uses and domestic uses, household uses, tends to have a much higher value than it does in agriculture, at least at the margin. Like if agricultural producers had to consider the fact that if they use water for low value agricultural crops, that water can't be used in industrial or domestic uses, they would take those opportunity costs a lot more seriously if they actually had to pay for that opportunity cost. And one way to get people to pay for the opportunity cost, or at least to see the opportunity cost, is to allow reallocation between sectors. If a farmer just has rights to a certain amount of water and they don't have any way of maybe selling that water to anybody else, they're just going to use as much of it as they can. They're going to use up their entire quota, their entire allocation, because they don't face any of the consequences. But if they had an opportunity, say, if there was a buyer on the other end of that transaction, like say a city that was trying to acquire water supplies for the coming year, if that city was coming to them and saying, look, we have a growing population, we have citizens that are going to need some of this water, we'd be willing to pay you, you know, $80 or $100 per acre foot for this water that you were going to use, which only had a value of $40 per acre foot. Then the farmer is going to actually think twice about whether do they actually want to grow that crop, or maybe do they want to, instead of taking the water, converting it to crops, and then converting those crops to money, just taking the water and directly converting the water to money. That's something that farmers would start to pay attention to those price signals if they were able to actually maybe profit from selling water to people that had higher value uses of it. So water marketing, I believe, is something that could really help eliminate some of the very low value uses of water, which are taking water away from other things that are much more highly valued. And I just want to talk just for a second about a couple different kinds of water rights institutions. Riparian water rights are rights to water because you own land that's adjacent to the water. Either you own land that's adjacent to a lake or adjacent to a river or a stream, or is sitting on top of a groundwater aquifer. Riparian rights are common in the eastern United States. So in the eastern United States, you're more likely to have rights to water when you own land that's sitting next to the water, or is touching it, or your land is abutting the water in some way, is connected to it in some way. Those are riparian rights. Again, those tend to be prevalent in the eastern United States. What's more common in the Western United States is what's called the prior appropriation doctrine, which kind of came out of the 1840s, 1850s gold rush, as people started moving out west and occupying that land, diverting rivers, using that water for irrigation and using it for other purposes. The doctrine that emerged out of that environment was that the first person to put the water to beneficial use is the rightful owner of the water. And as long as you continue, you know, if you get there in 1845 and you start to you withdraw 2 acre feet per year from the stream, and you sort of have you got there first and you've been withdrawing that amount consistently over time, then you kind of have that right to continue doing that because you were the first one to put that water to beneficial use. And there, you know, there's debates in the legal world about what it means to put something to beneficial use, but you know, basically just withdrawing the water and using it in some way is really all that entails. So what this means is that it's not a way of allocating water towards where it's most valuable. It's just allocating it to who got there first. And if there's no way of reallocating it, then you have perhaps some uses of water, some users of water that will get to put the water to use in some way just by historical accident, not because they have the best use of the water, not because they're using it in a way that's efficient or that's most valuable. It's just because they got there first. And if there's no way of kind of reshuffling the water around after those initial rights have been allocated, then you can have these things persist where you have a lot of water being used in uses that are not very valuable for society, just by historical accident, just because the person got there first, and there's nothing that can really be done about that. And that's why water marketing is so important, because you have these historical accidents of certain users getting there first, getting rights to water first, and eventually maybe other uses come along which are a lot more valuable. You'd like for there to be a way to have that water be able to change hands from those who value it less to those who value it more. And so in general, there's kind of like, we say that there's senior rights. Senior water rights are like the oldest rights, the ones rights of the people that got there first. And then every subsequent person that gets there and withdraws water, we say that those rights are junior. Those are junior rights. They're more recent. They're not as robust. They're not as guaranteed. The senior rights holders are entitled to their allocation. They're entitled to their full allocation, and only after they have their full allocation met are the junior users allowed to withdraw water for themselves. Just a simple example of kind of how this might work. You have farmers in the Imperial Valley of California that are growing alfalfa, and let's say that there's people outside of San Diego, there's farmers outside of San Diego that want to start growing avocados. These Imperial Valley farmers, they have senior rights. They get to withdraw water first. They have the priority. And if there's enough water, if there's enough rainfall, it might be the case that both the alfalfa growers and the avocado growers will be able to fulfill their entire allocation. But in dry years, for example, when supplies are particularly low, it might be the case that junior users may not get their full allocation. The senior users will sort of get their allocation first, and then there might actually not be anything left for the junior users. And so I have just a little graphical analysis to kind of show how this might work. Avocados tend to be a very high value crop, and so I have this is sort of the demand curve for water to be put to use toward growing avocados. That's what this blue line is. This is the demand curve. This is the marginal benefits of water in avocados. And then let's say that this is also for alfalfa. This is also the marginal benefits of water going towards alfalfa. But as you can see, the marginal value of water in avocados is a lot higher than it is in alfalfa. So I'm going to sort of use a similar kind of graphical trick, which we've seen a couple times before in this class, where the horizontal distance of this plot here, that is the total amount of water that's available, and we can consider how that might get allocated between these two uses. So this is like the total quantity of water that's available in a given year. We have, I took this alfalfa curve, this alfalfa demand curve, I flipped it around, I took the mirror image, and so water in alfalfa is increasing as you move from right to left. Water in avocados is increasing as you move from left to right. And if we use this example of alfalfa growers having senior water rights, they're entitled to the entire portion of their allocation. So they get to use water, and try to grow these crops, these alfalfa crops, all the way up until it doesn't make sense for them to do so anymore. All the way up until the point where marginal benefits for themselves is zero, if that's their allocation amount. And then the junior water users, which are the avocado growers in this example, they have to just use whatever is left over. They have to use the residual. Alfalfa growers get to use it as much as they want, and then the junior avocado growers get the leftovers. And so in that case, the avocado growers are just going to be able to use water up until this point, so they sort of capture the benefits up through here. But we still have so this sort of vertical line here is like the allocation. So junior users get everything to the left of this line. The alfalfa growers get everything to the right. And at that allocation, we have a lot of potential gains from exchange that will be possible if these two parties were able to trade with each other. The avocado growers would benefit a lot more than the alfalfa growers, and it would be inefficient for them not to be able to use, for example, use water up to this line, for example, and have like an allocation that would look more like where the avocado growers have water up to here, and alfalfa growers have water up till here. That's kind of the same kind of graphical and analytical approach that we've used in the non-renewable resource section of the class, as well as in the tradable permit section of the class. It's the same idea of allocating something that's scarce efficiently between two users. And the same thing applies to water. That the same concept applies to water, where you'd like to have a way for people who value the commodity or whatever it is, if it's the tradable permit or the non-renewable resource or the water, you'd like to have the people that value it the most use it up until the point where their marginal value is equal to the marginal value of the alternative use, which would happen sort of at this point where these two curves intersect. So for your homework assignment, you'll have an example of this. And the key thing you want to do, just the basic approach you want to take, is you want to equate. There's marginal willingness to pay in each of those cases. In the case of the homework assignment, there's marginal willingness to pay for water indoors, and there's marginal willingness to pay for water outdoors. And to get an efficient allocation of water between those two uses, you want to make sure that these two are equal. You want to find the quantity, find Q in and Q out, where Q in is the amount of water used indoors, Q out is the amount of water used outdoors. Find Q in and Q out such that this condition holds, such that the marginal willingness to pay for water indoors is equal to the marginal willingness to pay for water outdoors. And then you also want to make sure that Q in plus Q out is equal to the total amount of water that's available. In this case, it's Q bar, I believe, in the assignment. So you want to find the allocation that satisfies both of these equations. This marginal value equation, marginal willingness to pay equation. You want those marginal values to be equal, and you want the amounts that are used in each of those sectors to be equal to the total quantity available. Okay. I want to just move into a few issues of water quality. We've talked about quantity. We've talked about kind of the water budget. We talked about that on Friday. We talked about kind of the hydrology and the amount of renewable water that we have to allocate every year. We've talked about different ways of augmenting supply and trying to manage demand. We talked about water marketing just now. Those are supply issues, but water quality is sort of the other aspect of water resources that's also important. And broadly speaking, I think about water quality as there's sort of been three broad movements, three frontiers, three stages of water quality awareness and water quality management. The first stage was when people were dying at extraordinarily high rates from cholera and other kinds of waterborne illness in urban areas because their drinking water sources were contaminated with sewage and other kinds of toxins. And the very first thing we did, back in the, I think it was 1850s or 60s, in Britain there was a guy named John Snow. This was before Game of Thrones. There was a guy named John Snow in Britain in the 1850s and 60s that sort of realized that all these people were getting sick in London because of contaminated water, because of the sewage that was getting into the water, and that was what was the cause of the disease. There was different theories about disease coming from breathing bad air. There was different theories about the germ theory of disease hadn't really fully been developed yet, and so John Snow was a keen observer of events in London, and he was able to kind of find out that these drinking water sources were getting contaminated, and that was the cause of a lot of the excess death in London at that time, and so that started gradually becoming more widely known, and cities started putting a lot of money into cleaning up their water supplies, making sure that their water supplies were uncontaminated, treating their water to a level that was drinkable at a safe standard. And this allowed for the most rapid decline in mortality rates, perhaps in the history of the planet. Like this was like one of the things that allowed people to, like, one of the primary factors that allowed people to start living longer, starting in like the mid 1800s. So the introduction of piped treated drinking water and sewage infrastructure. There's a study from 2005 that tried to estimate some of these things. That those investments, those water treatment and sewage management systems, Cutler and Miller estimate that those account for about half of the total mortality reduction that occurred over that time period, about 3/4 of the infant mortality reduction, and about 2/3 of the reduction in mortality for children between, say, the ages of 1 and 5. And this was just an enormous human development, an enormous social development that allowed people to start living longer and not dying, very young because of waterborne disease. So these are some of the huge positive developments that have happened in water quality, and some of the first stage. You can think of this like the first phase of water quality development was to clean up drinking water supplies. Okay, the second stage is industrial pollution. So there was a period in the 40s and 50s, 1940s and 50s, I should say, where a lot of the rivers in the United States were polluted by industrial discharges. A lot of grease and other sorts of chemicals would be discharged into rivers and just sit there. And this is a picture from Cleveland, Ohio, where there's a train. This is a train tracks here on the left hand side of this picture, and the train, as the train would go by, sparks would kind of fly off of the train tracks, and occasionally some of those sparks would land in the river. And because the river was so nasty and oily and contaminated, sometimes the river would catch on fire, and you'd get some of these big river fires, such as this one in 1952. And after the introduction of the Clean Water Act, this was something that greatly improved surface water quality. And it wasn't necessarily like the drinking water supplies that were contaminated, but like the rivers and streams and lakes were sort of the next frontier of this water quality issue. And a lot of regulations were put in place to limit the discharges, limit the kinds of things that could be discharged and the amounts of things that could be discharged from wastewater treatment facilities and other sorts of industrial facilities. Those limitations were put in place in the 70s, late 60s and 70s. And those went a very long way towards cleaning up sort of the next frontier of water quality, which was not drinking water, but the kind of the quality of surface water, the quality of rivers, streams, lakes, things like that. And so in particular, we saw the Cuyahoga River. This is in Cleveland. And eventually the Northeast Ohio Regional Sewer District invested a bunch of money in cleaning up the river and developing new sewer systems, putting in standards on industrial facilities that were discharging to that river. And those things went a very long way towards cleaning things up. And here we have a picture of beautiful Cleveland, Ohio today. A lot of improvements since 1952. And then the final frontier is non-point water pollution. I don't know if it's the final frontier, but it's the next frontier. There may be something beyond it that once we take care of non-point pollution, then maybe we'll discover something else that's a nuisance, and we'll take care of that. But this is a very tricky thing. This is like, these are pollutants such as nitrogen, phosphorus, sediment that run off agricultural land that come from very diffuse sources that are spread out over wide geographic areas. And these are much more difficult to regulate than sources that have discharges that come out of a discernible pipe, that have a discrete pipe that the water flows out of. These are very hard to monitor because it's just it's diffuse runoff off of land. Okay, the Chesapeake Bay is one of the places in the United States that is suffering the most from some of this non-point pollution, in particular nutrient pollution. Again, this comes from nitrogen and phosphorus. And so once again, we have a case where we have a social dilemma. We have farmers, in Pennsylvania and Maryland and Virginia. In this case, it's a lot of dairy farming, especially, which causes a lot of this nutrient pollution. But these nutrients run off the land in southeast Pennsylvania, and they eventually make their way into the Chesapeake Bay. They cause algae to grow. This problem has been recognized for a while, but it's very hard to solve. There was initially the Chesapeake Bay Agreement in 1983 to try to limit these things, and it wasn't until 2009 that there was really a systematic attempt to regulate the loads that come from some of these non-point sources. TMDL, I should just say, it stands for total maximum daily load, which is sort of the only provision in the Clean Water Act that allows for the regulation of non-point sources. The problem with non-point sources is that there's not the same legal authority to regulate non-point sources the same way that there is for point sources. The Clean Water Act doesn't give the same kind of direct authority for the EPA to mandate practices on non-point sources, whereas they do have authority to regulate point sources. And so what happens with non-point sources is one of the ways the Clean Water Act is structured, and the wording of it is that if water quality standards in a particular state are not able to be met through point source reductions or through technology mandates, and if the water quality is not able to be brought up to standard through those measures, then a total maximum daily load has to be set, and the state has to develop some kind of implementation plan to reduce the total amounts of these pollutants that are running off into the water course in a given year. And you have to find some way of achieving the total amount of point and non-point pollution to be below that total maximum daily load amount. And that's what's currently in place for the Chesapeake Bay as of 2009. Now, one thing to note is that the costs of reducing nitrogen and phosphorus are very different for different sources. So they're very expensive if you want to make additional reductions in nitrogen and phosphorus at wastewater treatment facilities. Those are on the order of $20 to $50 per pound of nitrogen reduced per pound. Whereas the cost of reduction for agricultural measures, things like cover crops or conservation tillage. I'm writing these out because they're not really visible on the screen. Grass buffers, riparian buffers. Those kinds of things are on the order of a few dollars per pound. They're still costly, but there's something like $3 to $5 per pound of nitrogen reduced or per pound of phosphorus reduced. And so if you're going to try to achieve a total maximum daily load, if you're trying to achieve a total amount of nitrogen and phosphorus running off into the Chesapeake Bay, for example, you'd like to do it with things that are going to cost a lot less. You'd like to do it with things that are more on the order of $3 to $5 per pound, rather than doing it through measures that are on the order of $20 to $50 per pound. And so there's these systems of water quality trading that have been developed. They're still kind of immature. They're not completely in place in every area, and there's not as much trading as maybe we would like. But the idea with water quality trading is that the demand for permits comes from point sources who have mandates to reduce their nutrient loads under total maximum daily load regulations, and then the point sources have that kind of direct regulation on them from the TMDL, and they're able to satisfy those mandates either through upgrading their own facilities or by purchasing offsets from non-point polluters who can implement conservation practices at lower per unit cost. And the way that this is typically done is through a system called baseline and credit, where the non-point sources don't have the same kind of technology mandates or direct legal mandates under the Clean Water Act as the point sources do. They don't have the same kind of heavy-handed authority sitting on top of them from the EPA. But if a point source wants to avoid having a costly nitrogen or phosphorus treatment upgrade or abatement upgrade, they can purchase emission credits from agricultural sources who are able to make those reductions at a much lower cost. The problem is, and one of the interesting wrinkles about this problem is that it's difficult to define exactly what should constitute a credit from a non-point source. So what is the baseline from which we start to count non-point credits? Like what's the level? You think about some baseline emissions of pounds of nitrogen per year. Like what's that baseline where we start counting credits once you get below that baseline? It's not obvious how to exactly choose what that baseline should be. And I'm gonna try to explain why that baseline is such a difficult thing to actually define. And so we're going to consider a simple example of two farmers. We have Farmer Brown from our previous soil erosion case. This is Farmer Brown. I'm going to call him a good steward. He's somebody who has very, very good soil management, very good nutrient management already. He's what I'm going to call a good steward. And then we have James Harden, who's not a very experienced farmer. And I'm going to call him a bad steward. He's someone that doesn't manage his soil and his runoff very, very well. So let's say that James Harden is up here. He's the bad steward. He's discharging 1,600 pounds of nitrogen per year. Farmer Brown is he's a much better steward of his land. He's managing his runoff in a much more environmentally conscious way. He's got his runoff down to 1,000 pounds of nitrogen discharge per year. So these guys are starting from different levels, and the question is, how do you set a baseline from which these two farmers could start to generate credits that they can sell into the market if you wanted to design a water quality trading system? And it's actually a very tricky thing, and I'm going to explain why it's not obvious. It's not at all obvious what the baseline actually should be. There's three options. The first option for the baseline would be to set a different baseline for each farmer according to their level of existing discharges. So this would involve, if you choose option one, then James Harden's baseline is 1,600 and Farmer Brown's baseline is 1,000. That's one way of doing it. The second way of doing it is to choose a strict baseline that applies equally to both farmers. So you choose some uniform standard that both farmers have to achieve before they are able to start to generate credit. So that second option would be like if we set the baseline, say, at Farmer Brown's level, and you have to reduce below Farmer Brown's level before you can generate credit. So James Harden would have to start. He would have to get up to 1,000 before he even is able to start to generate nutrient reduction credits. That's option two. Option three is that you choose a relaxed baseline for both farmers, so that both farmers, their baseline is say as at a high level. Say that their baseline would be at James Harden's level, where once you get below James Harden's level, then all of a sudden you're able to generate credits and start to be able to sell your credits and get some money for your conservation efforts. Now, I don't think I'm going to get to the entire discussion of this today, but there's problems with all three. So let's consider the first option. Let's say we define the baseline at their level of existing discharges. So this would be 1,600 for James Harden, 1,000 for Farmer Brown. This has some equity concerns because we have in this case James Harden, which is able to generate credits starting from a baseline of 1,600. You'd expect, based on kind of the marginal cost of reductions, you'd expect those reductions for James Harden to be relatively easy, because the way that we have these marginal cost curves in pollution cleanup is that the first units of abatement are very cheap, and then the subsequent units of abatement start to get more and more expensive. So James Harden's going to have a very easy route to getting credits. Farmer Brown's going to have a little bit of a harder route because Farmer Brown has already been implementing some conservation practices to begin with. And so this kind of option, setting their baseline at the existing discharges, sort of advantages the bad steward. It sort of gives them more of an ability to make easy money before the people who have been already kind of been good stewards that have been managing their soil well all along. It sort of advantages the bad stewards, lets them kind of get paid for some of the early kinds of conservation measures that they get to adopt, whereas Farmer Brown has to go beyond what he's already done, and he may have already put in significant effort to begin with and not gotten paid for it. That's option one. I'll go through those two other options on Wednesday, but I think this is kind of an interesting kind of economic conundrum in the issue of water quality management, and particularly non-point source management. And so I want to talk about this baseline and credit because I think it's kind of a cool little illustration of how incentives matter and how designing policy for these things is very tricky, and there's a lot of trade-offs and disadvantages to any kind of system that you design.